All right. We're live for day 17 of Advent Code 2024. And today we're going to start by digging back into the history references. So let me pull that up here. Um, let's see. 2024 day 4. That's this year. We're skipping over a day 19 problem, but a day 10 problem. In 15 minutes, maybe we could do a shorter one. What did day 5 referenced? Day 5 of 2017? Okay, we don't think we have this one. So let's do that. Geez, I don't think I even have directories for 2017 yet. Okay. Um, day 17, 2017. In here somewhere. No, but it's not refresh. Oh, no, I don't even have it in here. All right. Okay, now you got it. Um, let's read the problem a bit, shall we? Okay. There's the typical story telling us we need 50 stars. Rules of the game. Okay, so we are stuck in a restricted area. You may only leave by solving a CAPTCHA, but you only get 1 millisecond to solve it. The CAPTCHA requires to review a sequence of digits, find the sum of all digits that match the next digit in the list, and the list is circular. Yeah, sure. Absolutely. Let's talk later. Um, the list is circular, so the digits after the last digit is the first digit in the list. Wait, what? I'm not parsing a day 1 problem. Okay, so we just have a list of digits. Looks like that. Find the sum of all digits that match the next digit in your list. Hey, Hellhound, welcome. How was your day 16? Oh, later. Okay. I guess we have an example. So 11122 produces a sum of 3 because the first digit matches the second digit and the third digit matches the fourth digit. I'm not getting the rules. 1, 2, 3, 4 produces 0 because no match, no digit. Oh, okay. So all the indexes where something matches the next digit. Wait, are we just grouping them? Um, 1 plus 2. Sum of all digits that match the next digit. Oh, okay. All the digits such that the digit as next matches it. And circular. Okay, I get it. I get it. Needed a heap queue to make part 2 work. Yeah. Um, I I basically just default to, well, I mean, the priority queue uses a heap. So I basically did do that for part 1. Heap queue is basically just Python. It's priority queue, right? I can't remember the import for that. But also, it's not so. Is it so big that depth first search wouldn't work even on part 2? I feel kind of ex-Pythonist. I mean, I used to do it a lot. I still have plenty of code on GitHub in it. I really like trying to make it concise. It was fun to do that with. And someday I'd like to do kind of a side by side, with some Python and Scala, do some refactoring and try and make them, don't write admin code style code. But try to do a comparison. Oh, good morning, Blue. How are you? Are you caught up yet? Oh, this is why I'm so confused. I changed my keyboard. Okay. Um, there we go. We don't quite want that. We want from resource. And this is 2017. I think it's dash 17. Okay. And we want to make it circular. Let's just add the first character to the end. Um, or, yeah, we could zip. We could do a sliding. I think I'll prefer a zip. Guess who has a work meeting at AOC release time? Oh no. I mean, what time zone are your colleagues? Maybe that explain a bit more. Okay, input zip input dot tail plus input dot head. Okay, and then we're gonna map. So we have 2 digits. So we have D D. We'll make this a collect actually. If we'll just call them A and B. If A equals B, then we just turn either of them as a digit, and then we get the sum. You're in Pacific time, and people involved are in India. Oh, okay. Yeah, that makes sense. They're like plus 15 hours from you, or 12 hours. Or just say I take that with me. What do you mean? Oh, take AOC with you? Just smile and wave, right? Oh, oh my God, this is a day 1 problem. Um, okay, I mean, that's the right answer there. 1111. Am I still misunderstanding something? That's 4. That's correct. 1, 2, 3, 4. Sure. Yeah, that's 0. 91212129. And that should just be 9. Answer was 3133. We're just summing digits. It's not even that many of them. Input dot size. PST is GMT minus 7. Yes. Right. Wait. EDT is minus 5. EST is minus 4? Or is EST minus 5? I don't even know my own time zone. Um, hey, do you see this? I'm stuck on a day 1 problem. This bodes well. It said it was too big. Answer is too high. Okay, I'm missing something here. Find the sum of all digits that match the next digit in the list. And it's circular. That's basically all they want. Um, all these tests go correctly, so I don't think I'm misunderstanding it. Does anyone see what I'm misunderstanding? So what I understand here, any digit that matches the next digit on the list. So here are all digits next to the next digit, right? And if they match, we keep that digit. And it's only one way, right? If a digit matches a 1 to its right. It doesn't go both ways. Otherwise, this here would be 6. Okay. Oh, is it time already? 5 minutes. Okay, I should have an alarm. Yeah. Is it distinct digits? No, because this should be 4. And that does result in 4. Right? All right. Well, I can't solve a day 1 problem. I think I should just give up tonight. Blue, how far along are you with your catch up? Did you get through day 14, part 2 yet? Um, there's no way. Okay, there are 3,000 of them. What's that times 9? Like that doesn't. There's no world where that overflows. Hey, Michael PC Gamer. You didn't get part 2, but you got part 1. Well, good, good. Did you end up doing a Dijkstra for part 1? I didn't stay through, but Day 40 part 2 was the most fun one. It's like a real puzzle, you know? Like you don't figure out how to, like you have to figure out what to do too, not just how to do it. Um, but this one here, I don't think I can even figure out what to do. Have you ever spent a long time with you helping you get through it? Okay, was that Gupta? Because I think I saw him in your stream. But good, good. Glad you got a Dykstra in. I had. So, did anyone solve part two yesterday? Sorry if spoilers. But I wanted to know if anyone solved part two without using a predecessor map. Like, I imagine you can do a full heat map and do the cost to get to the start or to the end. Do a few searches in various directions. Something like that. Okay, it's time. I failed 2017 day one. 1 minute and 30 indeed. Um, let's go back to day 16 and let's turn this into day 17. Um, oh wait, we didn't want to delete the input line. Hmm. Okay, good luck, good luck. I think today I'll read the problem a little bit more slowly. Make sure I have some good comprehension. Alrighty. I imagine. I imagine. Oh, I just went right down to the problem anyway. Initialize the registers. Ooh, registers. Run the program once it halts. Oh, okay. Wait, this simulating a computer opcode. Is this an encode thing? Feels like you're following. This is a reference to 2018 day 6. I just want to see what that problem being referenced is. Chronal coordinates. Yeah, I did this one not too long ago. Warm up earlier this year. Okay, so we have 3 registers and we have a program, an encode program, 3-bit computer. This program is a list of 3-bit numbers. Okay, okay. Um, 8 instructions, each identified by a 3-bit number. Okay. Is this basically just the encode from 2019? Computer tries to read an opcode passed into the program, it halts. So the program would run those instructions. Okay. Well, let's keep reading this. So 0 through 3 represent literal values. 4, 5, 6 represent the 3 registers. 7 is reserved and later, I guess. And 8 instructions are as follows. Advance. Performs division. Value into A register. Okay. Let's just start implementing this machine. So okay. So class, wait, how? How does it know? Like, did it look at the day 17 file that I downloaded? Okay, that's crazy. Um, anyway, yeah, sure, we'll call it CPU. Um, and it has registers. The program will run it through in a different way. So, and I perhaps has memory. Um, so A, B, C. And what's stored in there? I'm just gonna say ints, maybe bytes. Okay. And we have various operators. So advanced instruction, the ADV instruction performs division. The numerator is a value in the register. The denominator is found by raising 2 to the power of the instruction's combo operand. Okay, what literal operand value of the combo operand can be found as follows. Okay. And we are going to go to a new CPU state. So these are all kind of like next functions. So this performs division. Val num is A. Val denominator uh, is going to be combo. So let's figure out combos. Def combo. I guess it gets a byte. We got triple question mark that for now. I think we need a program counter. So we'll do PC. Okay. No, it's not just combo. It's um, 2 to the power of the instructions combo operand. So 2 to the combo. So an operand of 2 would divide A by 4. Okay, yeah, which is 2 to the second power. All right. And an operand of 5, representing the B register, would divide A by 2 to the B. Okay. So when it's done, the result of the division operator is truncated to an integer. Integer written to the A register. Are these all integer values? I guess these are integer values now. Just the instructions are bytes. I got it. This is a 32-bit computer then, with 3 bits. And okay. So right, that's a result. We truncate it into an integer and copy that to A. So copy A equals numerator over denominator. And that's our new CPU state. Well, the J and Z instruction, def J and Z, does nothing with the register. So this is jump non-zero. And I'm going to turn off Copilot here. Okay. If A is 0, then we do nothing. Otherwise, we jump to set the instruction pointer. I guess program counter is instruction pointer, so we'll rename that, rename PC to IC or IP. to the value of its literal operand. So literal. So combo and literal. Gotta implement those. So we copy and IP equals literal. Okay, I like this problem. BXC calculates a bitwise XOR of registers B and C and stores it in B. Okay, def BXC. Just go straight to copying. B is going to be B XOR C. Okay, the out instruction, def out, calculates the value of its combo operand, modulo 8. Combo mod 8 and outputs that value. What does it mean to output that value? Do we just print that? Okay, the program can output multiple values separated by commas. I think we're going to store output as well. But this is just a vector. So we copy. Okay, CDV. Oh, I'm still writing all of these. CDV looks exactly like the ADV instruction, except the result is stored in the C register. The numerator is still read from the 8 register. Okay. Val noon. Bro, I'm still reading the problem. That was fast. Nice. Wow. Denominator is 2 to the combo. And we copy and store it in. Oh, so it means A divide, B, C divide. So C gets the division. Numerator over denominator. Okay, great. I have those all implemented. Oh, we're making this a case class. Okay, and the operands. How do the operands work? 8 instructions, each define. Yeah, each instruction also reads a 3-bit number after it as an input. And this is called its operand. Right. So def next. I guess we have to pass in the operators. Or we'll pass in the input. So the input is the code, which uses switch case and doing all operations in a loop. Yeah, I mean, even then, I haven't even written out all my operations yet. How's part 2 looking? Okay, so opcode is 0, operand is 1, opcode 2, and there are 2 types of operands. So we have op int, and then I don't know, we'll call it input argument. We'll call it opcode. Opcode and operand. Okay. So that I misunderstood. So we'll do an opcode and match. Um, zeros advance, and we do that through 8. Um, well, we advance. And we do need to pass along the input to each of these. So every operand can be combo operand 0 through 4 represent literal values 0 through 3. Or 0 through 3 represent uh, 4, 5, and 6. Okay, so combo given a number. I should use enum, so enum opcode. We'll comment that for now, so it's still compiling. So we have advance, BXL, BST, JNZ, BXC, and out, and BDV and CDV. Okay, out, BDV, CDV. Okay, and those should all be numbered basically 0 through 8. Since I'm doing opcode match, we do opcode that from ordinal, opcode, right? And now we can just do a full exhaustive match. Oh, this is weird. Worksheet dots, we don't need that. Looks not breed forcible. Fun, cool. We have a fun problem tonight. Okay, so I might inline these definitions because we do combo. Okay, so we'll do combo based on some operand. Let me just do that for now. Okay. So we define combo based on operand. And it's just, we'll match on that 0 through 8. Literal value 0. Okay. Case 1 is 1. Case 2, 2. Case 3 is 3. 4 is going to be A. 5 is going to be B. 6 is going to be C. Case 7, we don't know. That's invalid. Okay. Great. Maybe let's do this given operand. And it's going to use. Yeah, play with implicits for no reason. Okay, now we'll copy these over, these implementations. So the ADV, uh, uh, jump non-zero. Wait, what's BXL? I don't think I even read those. BXL? I must have mistyped. That must be BXC. Yeah. Okay. So B XOR C. Um, BST. I don't think we did this. So BST calculates the value of its combo operand modulo 8. Right set to V. So copy B equals combo mod 8. Jump non-zero. We've got that. Wait, there is a BXL. Whoops. Okay. This here is BXC. Okay, BXL. Opcode 1. Oh, and we missed ADV. I missed two opcodes. um, oh no, we did do ADV. So BXL is bitwise OR of B and the literal. Okay. I don't know, val equals operand. Just so we can say literal. So B XOR literal and stores that in B. Copy B equals that. Okay, BXC, BXL, BST, right? J and Z. BXC is done. Out. Um, with our output. Next, does a CPU and the output, if any. Right? So this just does this, and then the sum is combo mod 8. Okay. Everything else goes to none. Okay, BDV is like ADV. Oh yeah, so we just have ADV, same things, and CDV, except numerator is B and C. All right. Okay, we've written out all the instructions. Geez, writing just writing out all the instructions took a second. didn't. But yeah, that works. It compiles. Now let's parse our input. Okay. So now our original A is going to be well, let's do it this way. We'll parse strings. So register A, and let's call it A equals input 0. So we have a start state, right? And it's going to be a CPU. Well, so register B, and this is input 1. Val register C, input 2, and then program. Um, this is line 4. Okay, so we have CPU. Oh, it's going to be defined outside because we're just defining a CPU there. So CPU A.2 int, B.2 int, C.2 int. Honestly, I could have just copy pasted this from my thing. Oh well. Okay, we take program dot sliding. We take two at a time. Oh wait, we split first. So dot split on the commas, map as digit. Oh, let's split, make that back into string, and then map as digit. There we go. Um, and we take that sliding 2 by 2, and we can just fold left, or let's scan left so that we keep all the intermediate output. So scan left with start state. And we take CPU.next given. Hold on, it's not just CPU. Right, so we have our state, and then we have, I guess, our list. Let's make this a list. So a list of code and operand, right? Let's call them A and B. And we'll do a CPU.next with A and B, exactly. And what do we do with this output? So val next and out. determine what the program is trying to output. Uh, let's see. Let's just do a buffer, a list buffer. Collection dot mutable dot list buffer of so out dot for each list buffer plus equals, or rather plus the out. Um, and then we just have the next state. Great, and val ans 1 is going to be the output separated with commas. So make string with commas. All right. Part 2 sounds like a fun night. List buffer dot empty. And CPU, it's missing another argument. IP. Oh, hold on. Instruction pointer. We need to get the whole program in memory. Okay, we need to get the whole program in memory. So there's no output here. IP program. It's gonna be a vector of int. Okay, so next doesn't take arguments here. We can do def given, and this depends on the IP. So combo, or no, def combo. This isn't using an int. It just does program I plus 1. Great. And the instruction counter always advances by how much? Just 1 every time? So operand, we can't pass that in as a function. Val literal, so we have def literal is just program I plus 1. Put combo up here. Okay, so that code shouldn't break. And we have combo defined, so that should work fine. And when you calculate next, we don't pass opcode as a parameter. So we just do def opcode equals program at IP. And we do opcode from ordinal. Okay. So this whole thing we can just do is opcode match. And then after this, well, we also need to update the program counter, the instruction pointer. So where does the pointer move? Is always just increased by 1, increases by 2 after each command it processes. And then of course it can jump. Okay. So it's the only case where it doesn't jump. Um, let's say increase equals this dot copy with what? IP equals IP plus 2. Okay. Okay. Only 30 people have solved part 2 yet. Can still be top 100. Okay, let me just speedrun this. I'm down. So I'm taking longer, but I'm hoping I'm setting good infrastructure down for part 2. Because this lets me go forward and backward through computer state as well. Because I'm not mutating anything. So after we copy, we're gonna increase. Let's say advance. Rename advance. After jump and Z, we don't advance, right? Let me make sure about that. The A register is not 0 jumps. If this instruction jumps, the instruction is not increased by 2 afterwards. Okay. So let's do. So let's look at the next state. If A equals 0, then this, and then just advance, not advance. Otherwise, we copy, set the instruction pointer, and that's that. And I know. CPU, let's say state. So state goes to none because there's no output. Well, I think maybe it's a bad design decision doing that with the whatever, because output's only ever really used here. Great, everything else only needs to jump, not advance. This dot advance. BF apparently is useless here. Trying to think about STHDiff. BF is useless. At first. Okay. Now where are we here? The CPU does also need the program. So val program value is just going to be the split as digit 2 list. 2 vector rather. Okay. Now we run this. And how do we know when we halt? Um, halts. The computer tries to read a lot of code past the end of the program. It instead Alt. Okay. So we just take as long as the instruction pointer is within the range, right? So to calculate all the states, we have our start state. We're just gonna do iterator dot iterate starting from our start state, and we just do dot next, and then take while CPU dot IP is in range. So let's see. Well, let's add a running method here. Def running Boolean. So this is program.indices contains IP. Okay. So dot next and dot take while running. Oh wait, this isn't just that. We have our output. So CPU val s out. So we'll just return the state, but we're gonna out dot each we're gonna add to the list buffer. State lb adds whatever that is. So this gets pulled the structure from the CPU and then state to move it along. Um, and I'm gonna put this on the run method. So def run. So this is going to return an output, a list of int, and then we're gonna return like a list of states. Um, right. Let's not return that until we know we need it. Um, and we don't even care about the final state. We only really care about the output. So dot take while running. I know, consume it. And then out dot to list. Okay. Great. So I think we have our solution. At this point, we just IP fix any syntax errors, fix any bugs, program value, required int. Oh, IP always starts at 0. Whoops. Wait, what am I changing? So I'm missing the IP. Okay, not found I somewhere. That's IP. Um, CPU.next right there. And the list buffer. Oh, right. It's actually called out. How are we going to name these? So we'll rename that to O. And just rename this to state. We can rename this to output. Um, and then the answer is that list of output. So val ans1 equals run dot make string separated by commas. Zani, hello, welcome. And Dinosaur, welcome, welcome. I haven't seen you two around. Um, oh, are we running infinite? I mean, we can take something like this and advance it one step at a time. So let's take our start state. And what does that give us? Oh, hold on, we can't be running yet. And let's try on an example actually. So here we go. So this is day 17. 2024. Okay. Oh, they don't really have an example where we can step through one at a time. I guess we have to step through kind of ourselves. Okay, well, we have a start state. Um, and let's just read our program and figure out what it does. So 0, that's ADV. So we divide the numerator, so we divide A by the combo operand. In this case, 1 is just the literal 1. So it should still be 729. Oh, wait, no. Divide by 2 to the 1. So 729 divided by 2 to the first power. 2 to the combo operand, literal 1. And the instruction pointer is not 2. Why is it 243 though? 729 Divide by 2. Did I do it? Divide by 3. Why are we dividing by 3? We're apparently dividing by 3. 2. Oh, wait. This is not what I think it is. This is an XOR. Um, okay. Math.pow. Uh, that exponent. Nope. Um, good list.fill. um, number of times is going to be combo number of times 2 and then product. Okay. I'm just doing that because I want it to remain an integer and not use double. Um, let's see. I need the real errors. What's the real error? Oh, there's no real error. Okay. 364. Okay, I mean that looks good. Great. I mean now that we're not XORing, let's just run this. Hmm. Okay, when we run this, we get 46353 521. So in the example here, 4635. Okay, that's working. And we just need to make sure, so we're printing all these outputs. We just need to make sure they all get actually added to the buffer. That seems to be the case. A list buffer, I think just 2 lists is how you do it. But apparently, I'm getting an empty list even though I get all of those. Okay, output for each. I'm not attaching it to the list buffer somehow. We could also iterate this in another way where we do actually just, I'll comment this out real quick because I have a nicer way to do this, I believe. So let's do an unfold. And we have our start state. And then we have a next state, yada yada. And option.when, as long as, so O gets output this way, this just becomes an output here. Output equals that. So as long as we are still running, s dot running, the next state, you return O and S. Okay, oh, look at that. Isn't that so much nicer? It's basically built for this. In fact, I'm gonna switch the order of my outputs here in my CPU state. So we're gonna do an option int and then CPU. So the state is on the right. Oh, Output's on the left. Whatever. We're not going to do that right now. Maybe a nicer factor for later. So we do switch around the order. And then oops. Leave that commented out. So we're going to take the output dot flatten dot make string. So to list flatten make string with a comma, and that's our answer one. Okay, great. Let's do that on the problem. And the thing is, I can highlight this. I can't copy it, even with key bindings. I don't know what's up with that. I do have to debug that. So we'll copy the worksheet output. Crazy problem, huh? Hey, well, I'm about to hit part 2, so maybe I can actually get ahead of you. How about that? Am I gonna have to manually type that in? Fine, I'll manually type it in. Jeez, okay. 4,6. Is it gonna take like reverse engineering? Oh no, no, no. Oh wait, this is still running on the example. Did I overwrite day 17.txt? No, no, that's still that. Whoops. Oh, okay, so it runs an example. I think it's failing to run on the actual thing. That's what's happening. That's why I'm still seeing the old output. Mm. Okay. Well, I want to cancel that run. Um, well, the old output didn't find the wasn't enough to test for the bugs. So I guess I have to do some manual looking here. So I suppose I could swap the order of these. Or we could swap after the fact. Um, state out. And we'll take state out and swap it. Okay. I'm only doing this because for my unfold, I want to just write you gotta swap the order of these. CPU.next. Hmm. Okay, let's switch back to the example. Maybe we'll mess with stuff to debug a little bit. Okay, not doing not doing BF. I believe you. I believe you. I could rewrite this slightly, but why is it not running? Indexing, compiling. I bogged down my worksheets somehow. They're not supposed to be this slow. When the next state is still running, we do cpu.next. Okay, so this gets us that answer that we're expecting. Wait, what if we were to say cpu.running? That should result in a bug, right? Um, well, it'll only not be running when there's no output. So it'll fail to result in any output. So when opcode fails, let's make this an option. Option when running. We do that. Otherwise, no, 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 no. Let's not mess with that right now. So when S is running, we give the next state. Yes. Okay, I'm gonna try and run this on the main example. And I'm just gonna read over this while that's happening because I think that was crapping out, but I don't trust my tool anymore after, was it last night I still don't know if it's running or not. Tried a performance optimization, removed the performance optimization, and it was actually working. So something subtle happened while I was editing, I suppose. Okay, this timed out. So we must be forgetting to advance somewhere, right here. When we do BSD, not advance. Okay. Okay. So this should be, is this my answer? 4635. Nope, nope, nope. It's still showing the old one. Um, is it trying to run again? Okay. And it's probably in a loop if it's not advancing. So in each of these cases, it's advancing, except for when we have jump non-zero. Advance, advance, advance. Okay, it is advancing everywhere as far as I can tell. Um, okay, CDV, C divided by 2 is a combo. Cool. BDV, same kind of thing, but it's B. Oh, wait, wait, wait. A. Here, that needs to be C. Copy paste error. Okay. B and C are happening properly now. Um, so is that tempting to evaluate? I don't know if it is. It doesn't seem to be running. Code lens generation. I'm about to stop using worksheets. Okay, evaluated. Is that right though? It still seems to be the same answer, or the example answer. Fun fact that I can get into later. What I've implemented here with next is basically a state monad, and you can unfold the state monad to get um, all the output. But that's a fun story for another time. Maybe later, another day, I can re-implement this using a state monad. Okay. Hey, I mean, it seemed to run. Uh, right. When I do this, however, that tells me it's running infinitely. Um, okay. Not a lot of way. Oh, here, out. When we hit out, no, we do advance. Um, BDV is B divided by yes. Um, geez, I'm gonna take out this indirection here. B divided by 2 to the combo. I don't know why I did that, Noomden. Uh, keep it close together. It's easier to read and debug. Okay, same thing with ADV. Um, whoops. A equals oh, wait. Okay. Right. That's not 2 to the combo. Frick, that's still XOR. Okay. You got it. Awesome. Did you uh did you point? So, stop fill combo 2. I don't really want to be writing that. Let's just do math.power. Math.pow. 2 to the combo dot 2. That's what we're writing. I found my bug. So this now equals B. Let's B over that. Today is painful, so you're just happy to finish. 282. Hey, 282 is still good. 266. Okay. Yeah, I have my answer. 0, 7. How tired do I have to be to write to write XOR instead of exponenting? 4, 2, 7. I feel like I haven't done that in ages. 0, 7, 2, 6, 4, 2, 7, 2, 5. I missed one. I tried to type it in manually. Well, let's copy the worksheet output. Go to Scratch. Okay. And it's probably gonna make us wait, right? 32 seconds left to wait. Probably yours was reverse engineered. Okay, cool. I'm looking forward to doing some kind of reverse engineering problem. This was like, we had a problem like this last year. Um, super fun. You had to draw a graph and figure out that was, uh, I can't remember the details, but that was super fun. And we had one on day 24 of 2021, like that. Okay, so this, I printed something. Uh, it was not the right answer. After accidentally putting in the example input. Um, okay, let's make sure the example still works. Oh, right, the example was working earlier. 46356352210. 46356352210. Okay, the example still works. So just another subtle bug. Oh, 272. I believe it. I believe it. I don't feel like I would have even tried brute force. So combo 033. 4 is A, 5 is B, 6 is C, 7 is reserved. ADV, Holmes division. Yeah, 2 to the combo operand. The result of division operation is truncated to an integer, then written to the A register. Okay, 32-bit, right? So we don't have any issue with that. BST combo operand mod 8. Yeah, goes to the B register. BXL, B takes the literal. Okay. B takes the literal. BST calculates the value of its combo operand. Oh, wait, we just checked that. J and Z, jump if not zero. Perhaps we have an error here. State A is 0, then this dot advance. I mean, so one nice thing about I can get a list of all operations that happened. Since I maintain here a list of all my states. Um, JN0, now BXC, bitwise OR of B and C stores in B. B equals B XOR C. Okay. Right. That's like the BXL from above. Aha! Eric Wassel has showed up. Due to the 64 cores, brute force would work. Okay, I believe it. It does seem like a fun problem. I've I've enjoyed these problems in the past. Um, I mean, so the fact that we're halting is a good sign, right? I think if we had a bug in here, we probably would not be halting. So perhaps there's an issue in my output. Perhaps I'm not getting all the output. If the next state is running, then we can do CPU.next and continue the cycle. We're not skipping over instructions somehow, are we? So we have a CPU state. We get the next state and the output. I should do that. Mm. Oh, right. 7264275. Let me look at my output code. We are outputting the combo operator truncated to 8 bits. So what is that called? Dot out. Outputs value. If a program outputs multiple values, they're separated by commas. Um, okay. We could check our combo operand just to be sure, but I mean, that's really straightforward. Most LLMs as a service are multi-step. Yeah, I think so too. You don't think about LLMs when designing puzzles. Good. Eric, you should add like a CAPTCHA to the global leaderboard. Make sure they're human. Um, I failed at a CAPTCHA, at the CAPTCHA problem from 2017 day one. I started with that as a warm up. I don't know what's wrong with it. I don't. It's a day one problem, and I don't understand it. I mean, I joke. AOC is basically, these are all basically kind of CAPTCHAs. These are really hard CAPTCHAs. Yes, LLMs have a human in the loop. Um, what it's trying to output. So I think I'm able to output, right? I'm able to output because I'm able to get this. Um, and perhaps what's happening is we are halting early. We're not getting all the output. So we are halting. How are we deciding to halt? So we get the next state, but if that next state is not considered to be running, then we don't output the current state. Oh, we are missing one output. I see. I see. Okay. Let's just rewrite this here. So when so we get the next state and the output from the current state, right? So that should go here. Um, as long as, well, I guess the current one was running. So if the next state is running, we've outputted sure. But what if the next state is not running? Then we fail to output this. Um, so we shouldn't check. We shouldn't check if the current state is running. If CPU dot running then oh, it seems so obvious actually. CPU dot next. Okay, okay. When CPU is running, CPU dot next. Makes a lot of sense, doesn't it? Great. So we let that run again. 2725. We're still getting the same thing. Um, I wish the example told us how many states ran so I could just verify against myself there. Um, yeah, if CPU is running, then we can do CPU.next. CPU.next is not valid to call at all if the CPU is not running. So there would be no next state to do. The start state.next. Oh, I think we're just testing things. So we have our start state. I think this is now more accurate. We're still actually getting the same answer. Um, I don't know. If we take a list of states, let's get output.size. Oh, hold up, hold up. We don't want. We want a list of states. So val states or oh, 72, right. This is like the output iterations. So iterator dot iterate. Let's make this a lazy list. Lazy list dot iterate from start state, and we're just gonna do state dot next and throw away the output. So we get all the states. Okay, now we can explore this. So states. Let's look at the final state. Where are we on state 72? Right, if there were 72 outputs, 72 is what gave us the last thing. So this state here, is it running? Running. False. Right, so nothing else should go after that. Oh, you found the code. Good, good. But future reference, you can bang AOC. Oh, time for breakfast. Okay, Blue. Thanks for stopping by, and see you tomorrow. And we can do states dot take while running dot size. So we know how many steps happen. And I'm of course 72, right? But let's see what is happening then at 71. So at state 71, so this should be running. I want to do 71.next. Okay, so this had nothing as an output. All right, and that makes it. Let's take a look at all. I'm going to list this. Okay, right. So we can see what happened here. Nothing, nothing, nothing. And at some point, we get outputs, and the very last one is a none. So it's not like we're terminating too early. I don't think. Let me check my running code. Program indices contains IP, right? Instruction pointer is within the indices. There's no room for an off by one in there. That's why I like to write the code this way. Um, okay. Well, we could print each of our states and try looking at this manually. I don't want to look at it all manually though. Um, okay, let's look at this. Let's look at each of the states. States.map. For each of them, what is the opcode that's about to run? Um, oh, that's infinite. Take 72. I think we can do a dot take while running, right? That should work. Now we can to-list that. Oh, and 72 should not be running. But it is kind of like our final state. So these are the operations that happen: BST, BXL, CDV. Um, let's print those next to their instruction pointers. Wait, the very last one is a jump non-zero. That's interesting. I think maybe our jump non-zero might be wrong. Uh, take a look at that. JNZ. It does nothing if the A register is 0, but it still advances, right? Um, if the A, wait, no, if the A register is not 0, wait, if the A register is 0, then we advance. We just advance normally. If this instruction jumps, the instruction pointer does not increase by 2. Is not increased by 2. Okay. Um, let's see. So state 71. I don't think I need to. Oh, running. Okay, so let's take a look at states 71 dot opcode. Oh. Okay, so state 71 dot opcode, but state 71 dot instruction pointer is at 14. And where would it end up jumping? So it should jump to, well, it depends on A. So state 71, it's the value of A at that point. The value of A is 0. So it should advance. So states 72. Could I summarize my situation? Sure, sure. We have output. The example works. And we have some sort of output for the actual problem. But this apparently is not the answer. And that puzzles me because I would have expected that bug would either cause instruction pointer to go awry and we have an infinite loop and it just doesn't run. Or I'm not sure what I think the nature of this bug might be yet. The other examples, um, the other examples. Oh, oh, right. Um, no, I haven't run through all these examples yet. So I suppose that would be helpful. Yeah, okay, I'll do that. 72 has no opcode. Let me just finish this thought. I just want to know the instruction pointer at 72. it's 16, and I want to know the program dot size. So start state dot program dot size 16. Okay, so that does jump to the end. No, because it's 0, it just advances. It just advances to the end. Otherwise, I guess it would be jumping, um, depending on the value that I don't know what jumps based on. Literal. Yeah, the literal value of the next argument, which I suppose start state that program 15. Probably just set back to start. Yeah, so that's a loop that sends it back to the start. I see what this program's doing. Okay, great. Well, there are simpler test cases, so let's use them. Thanks for pointing out that those exist. Uh, okay. So what is all of this start state? Let's go, we'll put tests down here. If register C contains 9, the program 26. So CPU, uh, well, we'll just copy our start state and, just copy all of the values of those registers and modify what we need. So start state dot copy. C equals 9, and the program was a vector of 2 and 6. That should set rest dot next, and we ignore the output. Dot B. Okay, so that should set register B to 1. No, I have a subtle bug because I'm getting unanswered is halting. I think we're halting too early. Um, yeah, I'd kind of like to decompile the program a bit. Oh, I mean, reverse engineering for part 2. That's exactly what we're gonna do. That part will be fun. So, okay, that checks out. So if A contains 10, the program 505154 would have output. So program, I don't know which operation it's from yet. I mean, let's see. I do have a list of the operations I run. There's always an out before a jump non-zero. So I think maybe we're ending the loop too early, or maybe not early enough. Uh, Probably because what is J checking the literal value of the next thing? Oh, no, it's checking what's in the register. So an ADV is somehow getting the wrong. Yeah, I'm not going to decompile that. But decompiling it would be one way to debug, I suppose. So 505154. Okay. And to get outputs, hold on. We need to get like an output def. So let's do run to get the output. So run state CPU, and we have a list of int, and it's going to be basically this minus some of the copy paste. So we have that state. When running, CPU gets next to list. Maybe I'll, yeah. Okay, so this new program, when I just run it, hold on, I have an error somewhere. Oh, two lists. Maybe we just do the whole string. Now we can flatten just to get the outputs. Okay, so 012, great. If the register contains 2024, start state A equals 2024, program equals vector. Let me just copy paste that. And yeah, I'll run that. Oh, start state.copy, right? What do we get here? 42567777310, and register C would contain and leave 0 in register A. Okay, I need to have a better way to run such I get the final state as well. Are you jumping when I shouldn't? I really don't know yet. So I'm gonna use the restroom real quick. I'm just gonna leave this code up. And yeah, I'll be right back. Okay, so the other part of this is 0 is left in register A. So let's try. We had a state. We're gonna take. We're just gonna iterate iterator dot or lazy list dot iterate with that as our start. And then we just take that next and we throw away the output to get the next state. And then after doing all those iterations, we're going to do a take while running. And you just want the last dot A. So that should be 0. Okay, cool. If register B contains 29, so start state dot copy B equals 29 with a program. Um, 17 should set register B to 26. Okay, so it's this thing again. I should make that a function. I don't know, def final state. So start state and we're returning a CPU. Um, or wait. Maybe we should drop while running and then take the next. Yeah, we should actually be dropping while. Drop while running. Head.a. Oh yeah, and I know I wrote that twice. So this run, it's actually just get the output. So we can just ignore this for now. Val ends one was output dot make string with a comma, right? We can take that out. These tests I don't care about anymore. Let's get rid of that. This is the thing we tried, so that's wrong. Okay, so now these methods are output. So final state of a CPU, we basically do this. So start state, there's no copy though. Okay, so the A, well, we don't do that. Head.a. So now we could rewrite this as a final state of this CPU. A should be 0. Okay, so now we want to check. We did 2024. If B contains 29, it's set to be registered to 26. So final state. There's probably something more concise than writing start state.copy. We'd have like a default program. So B equals 29 and program equals vector. Uh, 17. So final state B should be 26. Wait, we have other issues. Output. Make string is not a member of CPU. Output is a list of int. We should be able to make string on that. CPU to list int. This is a function. Oh, wait. Output given our start state. Okay, right. So here was the A, here is the B, 26. Okay, if the register B contains 2024, and C contains 43690. Okay, so start state copy B equals 2024. C equals 43690. Program equals vector for 0. Um, and I guess we do the final state of that. Dot B 44354. Hey, so all of the example instructions pass. Um, all the examples pass, right? B to 4, yeah. This sets B to 26, sets A to 0, and have the output, meaning final state, up near output. Okay. This one returned 425,310. Okay, so it had the correct output. And then the one above it, A contains 10, and that program it should output 012. That's 012. And your tests weren't good enough to catch whatever wild bug you concocted. Thank you, thank you. Register C contains 9. 26 would set B to 1. Okay, cool. That just means I get to have more fun than other people would have. Right? This is wrong. 072642725. 072642725. I could try entering that again. I'm pretty sure I entered it. Okay. Great. I guess I'm gonna take a closer look at the program. In fact, let's try to understand it a bit. We're just gonna replace all the instruction codes with yeah. We're gonna replace we're gonna turn it into assembly from machine code, basically. So day17.text. Let's save this as reverse. Okay, so opcode 2, we have BXL 4. Wait, I should do this programmatically. Yeah, I have a way to do this programmatically. So we have a start state dot program dot sliding 1 step by 2. So that should be all the opcodes. Okay. And actually let's just no, let's do a sliding window 2, and we'll just print the whole decompiled program, right? So program.sliding 2 dot I don't know, for each opcode and then operand. I'm gonna call it arg, We're going to start calling it op and arg. Op, arg. And we could print line. So opcode dot from ordinal, op. And how do we do this? And then we're going to just print the arg after it. Oh, and this is going to be vector of 2 arguments. And I guess we have to do a case because we're destructuring it. Oh, wait. Let's do the actual arg. There we go. Okay, let's try to understand this program. I guess we don't really need this file. Maybe I'll solve part 2 before solving part 1 in the process of doing this. Okay, I need to figure out what these names mean. Let's try to, I'm gonna go over each of these and try to remember, give myself mnemonics. So this means A divide. We divide the combo, place in the A register. We divide by 2 to the combo and replace in the register. And we also have B divide and C divide. Great. So that's 3 of them. Should I count binary? That's 3 of them. BXL, bitwise XOR B and the literal. So B XOR literal. Okay. And we had another XOR, B XOR C. Okay, I can read that. BST. Why is this called BST? B state calculates the value of its combo operand modulo 8. Why would it be called BST? And the combo operand. B store. Oh, okay, right, restoring it. And then jump non-zero. Cool. Great. So B store 4, and that's a combo. It's always gonna be the value of register A. Maybe I should translate these. So let's say, well, okay, it could be interpreted as literal, but in this case, that's gonna be A, right? Or B set. Set it to the combo. Okay, that makes sense too. BXC, does it even use that value? It's just B XOR C. So in that case, that doesn't matter. Before I start messing with this, I'm gonna get a copy of this. And so we store A, whatever B and C are, we take the XOR and store it as B. B XOR literal, literal 1. Right, so it's just B XOR 1. Okay. And then BX literal 7. Okay, so we flip basically well, hold on. I'll try to understand that in depth more later. So C D5, so this is going to be C divided by 2 to the 5th. Okay. Right, because 5, right, C divide Let me make sure. 7 works exactly like the advanced instruction, except that the result is stored in the C register. 7 works like the... Oh, right. Anyway, the not advanced, A divide. Um, Raise 2 to the power of the instruction's combo operand. 5 represents B. Oh, never mind. So this was a 5, right? C to 5. So C divided by 2 to the 5th. I'll use Python syntax, 2 to the 5th. Or, we could just write that out in binary. No, not to the 5th, to the B. Okay, combo operand 5 represents the value of register B. Okay, out 1. What's the parameter of 1 do? Calculates the value of the combo operand, which in this case 1 is always going to be what? A literal 1? Oh, hold on. Literal values 0 through 3. Wait, have multiple operands? When you say literal values 0 through 3, let me see. Maybe I'm misunderstanding literal. Uh, yes, you're right. Wait. Yes, it's always A divided. Well, hold on. Yeah, I think I might have misunderstood the literal. I think I might have my bug. The value of the literal operand is the operand itself. Okay, but combo, 0 through 3 represent the literal values 0 through 3. Does that mean the 0th, 1st, and 2nd, and 3rd values? I mean, maybe I did. Value in the A register. Oh, ADV and BDV. Okay. ADV and B... Wait, what is the difference between ADV and BDV? So the only difference is that's written. It always divides A, but it's written to the A register. So this works exactly like ADV. The numerator is still read from the A register. Okay. I see. Oh, wait. I fixed that as a bug. I think maybe I read that earlier because I fixed that as a bug. I remember I was like, oh, I have a copy paste bug. Is this your bug from part 1? Yeah, I'm still on part 1. The thing is, I guess BDV and CDV. What's the example program? I guess the example program here doesn't use BDV and CDV. Do any of these programs use? I don't know. Okay. So you divide and set to B. Set B to the division. Set C to the division. That's how I'll read it. Okay. So our and's 1. You've got a value. I don't want to overwrite this because I was in the middle of decompiling. I'm gonna have a fast delta. So, copy this worksheet output, scratch 5, and and's 1 is a string. There we go. So part two, digging deeper into the device's manual discovered a problem. This program is supposed to output another copy of the program. Unfortunately, the value enriched. Oh, it's a quine. Wait, seriously? That's such a fun Easter egg. You designed an assembly language, and then wrote a quine in it. That's so cool. You'll need to find a new value to which you can initialize register A so that the program's output instructions produce an exact copy of the program itself. Okay, we need a new value for A. Uh, yeah, I think this is very obviously has to be decompiled. Um, no way I'm gonna try brute force that. I mean, these architecture problems have frequently been like decompiling, right? This assembly language is purpose built to Quine. Cool. The bug was my BDV and CDV. Um, so for BDV, I assigned the value of the B register to the division, right? This part right here that says the numerator is still read from the A register. um, I just glossed over that. So it works exactly like the ADV, except the numerator is still read from the A register. Or except that the result is stored in the B register. Yeah, it was that. Okay, but I can't be the only one. So aneurysm had the same issue. I see. So those tests can just live there. I'm decompiling. Thanks. I will. I will definitely enjoy part two. Okay. So let's start from the top again. Uh, A combo A is 4. So we set B to A. Let's write it. We're just gonna go to like C. B equals A. And BXC. Um, B equals B XOR C. Um, BXL1. BXL. Hold on. You know, I should be keeping the original things here. I'm just gonna write it next to. I do want to have this all in one block, so we are just going to write it next to here. So this means B equals A. B equals the operand completely gets ignored. B XOR C. Um, you tested 2 billion values so far. Someone's gonna use ASIC, something wild. Just because. Hold on, I have a dark spot here. I want to fix that. Okay, B equals times whatever the literal value is. Oh, so this is B XOR 1. Right. And then BXL7. I guess, yeah, equals B times the literal 7. I think I'm going to translate that to binary. 7, we could say 111. 001. Okay, so basically flip that bit, flip those two bits. So, I mean, it should still be the same program if we were just to make that 6, BXL6. Mhm. In fact, let's test that real quick. My note isn't quite right for BST. B set um, combo operand mod 8 and writes that value to the B register. Um, the combo operand, so the combo operand of 4 represents the value of the register A. Okay, right, A mod 8. So, and what does mod 8 look like in binary? I think it's basically masking, right? So it just takes the last 3 digits, the rightmost 3. Um, yeah, just gonna write these all in binary. There's another way to write this. How would you mask? I don't want to think right now. Needs more quick sort. I'm not there yet. C dv6, so C um, equals A divided by, yeah, C gets the value A divided by 2 to the, and what does 5 mean? 2 to the B. 2 to the B. And then out 1. Is it too long? Oh, sliding 2. We need sliding 2, 2. Okay, so every other one. I see. Yeah, that is weird. So, um, yeah, I thought it was weird that we had 2 BXLs in a row. So, well, every other one is wrong. Blip, blip, blip. And instead of 16, we should have 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, better, better. So B equals B XORing with the literal value 5, 2 to the 5th. So 2 to the that's 0, 1, 2, 3, 4, 5. Really? That's so big. 32. Why? So we're flipping the leftmost bit of a 32-bit number. I guess we're making it negative. 8. If these are unsigned ints. And then B equals B XOR. Okay, we're gonna say take right 3 bits. So B becomes the right 3 bits. Flip, it's, I'm gonna say the first bit, flip it's 1 bit. Yeah, 1's position. Okay, and then C gets 2 to the B. Okay, and since B is B is constrained now to 8 values. So we'll have to think about that. But that's what happens to A, and it gets stored in C. Okay, BXC. Um, Not that I don't mind this music. It's actually good music, but I do want something more chill, so I'm just gonna restart Lo-Fi Leah here. Okay, so B XOR C. And what was C most recently set to? We'll get there. We'll get there. So, um, advance and 3 gets no, A divide. A gets the value of A divided by, and 3 just means literal 3. Combo operand 3. Yeah. 2 to the third. And to the third is just 1, 0, 1, 2, 3. Okay. That's 8. And then out 5. Remind me how out works. Out calculates the value of its combo operand modulo 8. So combo operand 5. So B mod 8. Okay. And then jump to 0 unless A is 0. So if A equals 0, yeah, if A equals 0, then we jump. Or wait, unless let me double check that. Jump does nothing if the register is 0. If A is not equal to 0, then jump to 0. So we restart the loop. Okay, I can write that as like a while. All right. Larry NY is rated again. Welcome, welcome. So I'm solving part 2, as you might see. I'm puzzling through this and basically decompiling, reverse engineering our machine code. Larry, first one we know to solve part 2. I mean, I believe it. Larry's pretty fast, yeah? Wait, you didn't, did you just finish? Am I mixing you with another 0? With another Larry? You're not a 0. I see black, welcome, good to see you. Okay, we can think about what exactly that's doing. So A gets set to some value, right? A equals B takes the right 3 bits of A. A gets divided by 1, that so we shift A to the right. A divided by, this could be written as A shift right 3 times, right? And this is actually A shift right B times. This is shift 6 times? No, 5 times. Wait, that's weird. I need to double check that. So BXL5, the literal 5, so 2 to the 5th. 5 times? Hmm. Um, C divide by 2 b times. C equals, I don't know, A shift right b times. Yeah, I'm gonna rewrite that as A shift right b times. The divide really means shift. Um, flip it's 1 bit. So we take 3 bits, flip it's 1 bit, and then C. I don't really know how to interpret that. So C minus the rightmost 5b bits. Oh, minus this many bits. Um, okay. What programming language is this? I'm doing this in Scala. Actually, for everyone who's new, I should give you a tour of my part one solution, just so we know where we're coming from. Um, hmm. so I modeled this as a CPU, in the CPU class, and this doesn't do any mutation. So all of its state is here. So the register values, the counter, um, and the program itself. So I know it's running if the program indices still contain the counter, right? Um, this is a helper for the combo. It might give me the ABC and a helper for the opcode, right? And the opcode enums here in Scala, I just placed all the opcode names here so I could use them down below. And they're all enumerated 0 through 8 in that order, or through 7 in that order. So that works out handily. Yeah, and we advanced programming counter. So when we when we implement when we I don't know implement an operation, what we do is we copy our current state and we modify whatever needs to change. So in advance, I take all of our state, keep that except for the instruction pointer, which I increase by 2. Hence the this dot copy, right? Um, so I mean, an advantage of this, this is a bit more cumbersome to write things this way, but an advantage of this is that I have all my states. I can go forward and backwards, and look at the value of b at any point in time, right? Mm. Um, so we move mostly with this next function, which returns any output if there is some, but also returns the next state. So depending on the opcode, these are basically just implementations ripped right from the instructions. For example, jump non-zero. If A is 0, then we just advance normally. Otherwise, we copy, setting the instruction pointer to whatever the literal value is. And this literal helper will, just um, take that value from the program. Okay, so there's that. And using this, I think it's nice. You can do nice things like take every state here. Mm. Um, we basically just iterate by using next, and we're doing the _2 to drop the output because we had output tupled with the next state. So we could take all the running states, or we could take a particular state. So I can be like states. What happened at after 32 instructions, and what was the A value of that, right? And the A value at that point was 7408. Or we can states dot map um, A. In fact, I'm curious to see this. So we map A to list. I think wait, we're only gonna take 72 because that's as many as we have. Yeah, underscore tuple is a tuple accessor. So here we can see how the value of A has changed over time. Oh, so it doesn't change for a while. Doesn't change for a while, right? Because that's each iteration of the loop. And eventually it hits 0. And what I want to find out is for each of these iterations, what ends up getting output, right? So the shifting back and forth, I guess, I guess it's, let's see. The shifting back and forth must be, when I say shifting back and forth, I mean sometimes we're like looking at the C value up further up is actually I'm not sure. We wanna output each of the letters in the program value, right? So we should basically be incrementing. This should be incrementing and printing. Is this debug mode? So this is called a worksheet in Scala Metals. So it works in Emacs or VS Code, Vim if you like. And basically anything you write, it prints the output to the right-hand side. So I use these for admin of code. It's great for like, exploratory programming. Here are like all my tests, for example, from part 1 for all of those examples. Larry, of course, yeah, you earned your sleep. Have at it. And good luck with the rest of your admin code. Yeah, I had a couple of helpers here. So this is how we get our output. Um, unfold works in such a way that we can just write when CPU is running, we do CPU.next. And this will give us all the output from those tupled things. Like REPL-driven development. Yeah, exactly kind of like that. Oh, I used to program in Clojure, and that was working with like Cider and NREPL. Super fun. Um, in fact, that might be fun to do with admin a code or like these kind of problems. It's great. It's also great for exploratory programming. But yeah, you're just reminding me that I missed that. I haven't touched Clojure in 2 or 3 years. I had to. I got to use it. Well, sort of use it at work. I was translating a Clojure program into Scala because the company decided they weren't using Clojure anymore. Just a little bit sad because I would have enjoyed using some Clojure for work. Um. Anyway, so that was my solution for part 1, and for part 2, I'm still trying to understand. Oh, no, scratch 4. Yeah, I'm still trying to understand this program and what it does. So B gets set to the right 3 bits, and we flip its ones bit. And then C, it is A shifted. Um, I want to see what A is in binary, actually. Let's just take a look at that real quick. That's probably kind of key to our solution here. So, wait, what's going on here? Is this one of our tests? Okay, so let's take just start state dot a as dot to binary string. Okay, and we might copy this as an example. Sparkly dark matter, going to resume learning closure. Yeah, no, do that. That's so worthwhile. How are you learning it? Did you read any of the little books? I've read the little what's the logic one? The little reasoner or the reason schemer? Is that the name of it? Yeah, I read the reason schemer, which has an implementation of minicanren. Um, and I met the inventor of that at a conference. Um, so minicanren is like a little relational programming DSL. So after I read that, I wrote an implementation of it for myself in Scala. So you can see that on my GitHub if you're curious. You're at chapter 5 or 6 of Brave Closure. Okay. If you're familiar with core logic and closure, that is minicanren that's mentioned in the or implemented in the reason schemer. Super fun logic programming. I do want to do some streams sometime where I show that off, because it's a whole new way to think about writing programs and fun to implement and tinker with. Anyway, so there's some binary. We could use that as an example later. For now, let's keep understanding this. No, 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 you're at scratch 4. Okay, so we take the right 3 bits, flip its 1 bit, and then C is A shifted. I don't know what to say about that. I don't have an explanation, but it's shifted this number of times. So flipping its 1 bit, I know that turns 7 into 6, 6 into 7, right? Um, and then we have B to the, this is the 32nd power, right? 2 to the 5th. And yeah, I guess that just negates. Eventually, you want to learn core logic because you failed to learn Prolog. Yeah, core logic's fun, and I think it's pretty accessible. I don't know, it just feels simpler than Prolog. I mean, it's so simple you can embed it in the language very easily, right? Like you can straight up just write your own implementation. Um, there's a paper called MicroCanren, if you're curious, that you can do that from. So A is right, set to the value of A divided by, so if we just shift 3, I'm just going to change this to shift 3. So the three that were used in B are now ignored. So those 3 are only ever used to decide what to flip in B. No, they're only ever used to decide how much, how much to shift A. I see. So those 3 bits are used to decide how much to shift A to get the value of C. And we output B mod 1000. Wait, why does C even matter then? Oh, wait, we have a B XOR C here. Um, okay, we flip using C. All right, all right. What does that really mean? At some point, I'm gonna bring out the whiteboard so that I have a visual on this. We XOR B and C. So B meaning the first three digits of A, and C being A shifted B times and flipped like even odd. Um, so we take the first three bits of A, and we flip it by so and so many bits after that. We XOR it with so and so many bits after that, and then that's what we end up printing. And then this advancing A is just for the next loop. So for this to work properly, well, okay, so we at least know how many bits there should be in A, right? There should be 16 times 3, right? Yeah. You're pretty sure it's more insightfully written as A over 8? I mean, what is it? That's how I wrote it at first, and then I decided, oh, you know what? A over 8 is just shift 3. It feels, to me, it feels more insightfully written this way. But yeah, they are equivalent. Okay, so I get the idea here. I think it'll help to have a whiteboard and talk this over. So let's pull up the whiteboard and we'll use some example. We have mod 8 and div 8. It's very clear in the small example, but again, failed to transfer the insight. Well, mod 8 is just masking the right three digits, right? How would you write that in other operations? You'd be like OR. It's like OR 7, bitwise OR 7. Yeah, we're doing bit ops. So I agree. Like this should be so a mod 8. I'm gonna rewrite this. So this would be a bitwise OR 7, right? Take the right three bits. Or rather, let's write it that way. And this XOR, I don't really know what to make of that yet. But you know, we can reverse engineer this. So if the last output, let's see if we can get it just to do any number we want. So what was our program? Day 17.text. Okay, so the last thing it should output is 0. So to get a 0, what happens? We print b mod 8. Let's say mask by 111. I like that better. Um, so the last three bits should be 0 by the end of this. And the last time b was set was b mod x. So at some point it was 111 or bx or c. So C is always sort of going to be nothing else matters past this. So even though C isn't explicitly like masked, this here really just means take 3 bits, right? Mask is an AND operation. Yes, you're right. If we did OR 111, it would just be 111. Thank you. Thank you for that. Not that changes anything for me, but I think other people following along might be a little bit less confused what I'm thinking. Okay. Um, so we have to end up with a 0, 0, 0. And to do that, C should have been a 1, 1, 1. So we had a 1, 1, 1. No, 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 no. Yeah, and B would have been a 1, 1, 1 as well. So C and B would have both been 1, 1, 1. Let's put C here, and this is just B. Great. And how would we have gotten C? Well, let's see. Wait, I still don't understand this. Literal 2 to the 32nd. Negating doesn't really matter here. I don't think negate. I don't think that's the point of that. I don't see how this matters. Well, for our purposes, it shouldn't matter yet. Maybe you optimize your program for no memory allocation. There's about 5 million tests per second, but probably won't terminate. Cool, cool. Yeah. BXL. Let me take a look at BXL again. The big was or register B and the instructions literal operand. Well, the literal operand. So this is BXL5. Oh, that's not to the fifth. I was still in like DV mode. Okay, cool. This makes so much more sense. Um, so B XOR 101. Zahara Mini, thank you for the follow. Wait, hold on. Zahara Mini AI. All right. Uh, um, yeah, literal 101. So we just flip those two side bits. Um, okay. So B was 111 when it hits a C at 1 1. Wait, C is not necessarily 111. C is just the same as B. So whatever this is, C and B are the same. Um, so we don't know what C was, but they are same value. So let's just say like, I don't know, X and then X. And then before that, you're going to try to gain insight comparing yours to mine. Oh, like comparing the input. Isn't that cheating? You're not supposed to share your inputs. Hmm. Okay. Right, where were we? We are on our little graph. So looking here on the right-hand side, we XORed with C, and then we XORed 101. So we flip, I don't know, well, we flip this bit, we flip this bit. Whatever's in the middle stays there. I don't know if this was flipped for the C. I mean, we could like assume some value for C and just do something that makes it work. If you want to get 0, 0, 0, you should get a C that's 1, 1, 1. See if it's even possible to do that. So let's operate from that assumption and then try to figure out what's possible. So let's say we want C to have value 1, 1, 1. which means at this step here, when we're XORing them together, B is 111, right? And then when you XORed with 101, then B must have been 0, 1, 0, right? XORed 101. Okay, and then the value of C was taken by looking at A, move over to the right by B. So this is 2. Okay, B would have been, I'm gonna gloss over that real quick and skip to how B changes. I see certain operations are always there, at least in the example. Oh, but then there's XOR. Wait, are you telling me you have different operations? Like there are different quines? So oh wait, I would have thought that maybe the value of A is the thing that really changes. That's interesting. So everyone gets a different program. Hey, that's fun. Okay, so B, something happens to C, or something happens to set the value C. We don't know yet. But before that, B has its right digit flipped. So this is 0, 1, 1. So this is originally 3. And when it became 2, it got used to shift over. So this tells me that at this point, when we're printing a 0, the value of A would have to be what? 0, 1, 1 on the end. But to get C, when we're shifting to, C needs to be 1, 1, 1. So that doesn't work, right? I think we want to shift at least 3. It'd be kind of a pain if we had to make this work with, I'm not sure. Someone spent $81 earlier this month doing something like that. I heard about that. Yeah, I think I saw it in the subreddit. Like early on in the month, right? Like I don't think it was even a hard problem. They brute forced it just to just to see. Crazy. Okay, so for this to work, CSB 111. Well, we want C to be 111 here. Yeah, and that clashes because C gets set from B at which point? After the flip. From here, this is used to set C. Right? Okay. So in order to get 0, 0, 0, let's just guess and check out the values. There's only 8 to try, right? So these two have to be the same value. Can we get this to be 3? So if we mod 101, wait, we just flipped the right 2. So for this to be 3, it needs, wait. The end result should be something for this to be 3. So if this were 3 here already, so 3 flipping the right 2 bits, 3, and we flip the right 2 bits, that becomes 1, 1, 0. So let's say we had 1, 1, 0. C also needs to be 1, 1, 0. We'll erase some stuff. C would have to be 110, and that turns this into 011. So this means that the value of A would have had to be 110110. No, 011. 110011. So that's one way to make it work. But then after that, we remove these 3 digits and do like the next thing. Okay, but 0 is the last thing we should be printing, right? So before that, there's a 3. So let's try to get the 3 to work. I mean, we could try and think of basically if we make the number bigger. I wonder if smaller works. Like, can we have this work with a 1, a 1 shift? Okay, so we have 001 and then XORed 5, and that results in 100. So C needs to be 100. Great, so shifting right by 1, the value of A just needs to be 1001. Okay, A at 1001 will result, and we can test this. In fact, oh, you know what? I think we could totally just run the program on this number for like all 8 digits to figure out which ones work. And this becomes sort of like a tree search, right? I think we basically have what we need now, now that we understand what's happening. And we search from the end, or do we search from? Yeah, we could search from the end states. Let's just do one more step here. So if we're printing a 3, hold up, 00. Why did I write a 100 here? That's 4. This is a final value of 4. No, hold on. Nope, because you XOR them both, and then we get 000, right? But what if the last thing we wanted to get was, so that works for that and that. Suppose the last thing we wanted to get was a 3. So 011. And actually, this should work for like larger values. So here, the shift right was 3. Anything larger than that should work just fine. We just wouldn't know what's in the middle here necessarily. 2 doesn't work, but 1 works. 0? Would a shift to 0 work? I am curious, but I don't need to check that right now. I'll just put 0 as a question mark here. Shift 0. Do these anti-blue light glasses actually work? Um, I didn't get them because they're anti-blue light. I'm using them here because it does help. It's so bright here. I have these lamps on me. I don't know if it does anything on my health and my sleep, melatonin, whatever, but it is easier on the eyes. So these are rose tinted glasses, and I got them just to have perspective. just to make myself more optimistic. But they are super fun to wear. Basically, if you put these on, sunset starts at 2 p.m., so you get like an earlier sunset. Super nice on hikes and nice with the snow, just whenever it's like really bright out, you know? Ah, thank you. Thank you. I blame the glasses. Yes, yes, this is Eric Wassel, the Eric Wassel. Um, Great. So we have three. How do we print a three? I just want to print something that's not a zero because it's a little bit different. So to get a three, yeesh, I don't even know. So whatever this is, XORed with five. So there's gonna be an XOR with five. Um, should this is gonna be the shift on A, whatever is in here, right? Being XORed with five. Well, we try a number. So let's say we want a shift of three. Um, if we want a shift of three, then what has to happen? So we XOR it with five, and here we get one. The middle stays the same, and then zero. This gets flipped. 110. I mean, kind of like reverses it. Ah, XORing at five reverses a bit. Yeah, I'm gonna write that down. Reverse the number, the byte. I don't know if it matters that that's reverse. I'm just accidentally thinking that. um, so for this to work with three, um, let's see, we need to flip the left side and the right side. So three needs to be 101. So the value in the A register needs to be 101. And this, there is a, wait, hold up. I think I'm missing a bit. I think I'm missing this bit where we flip the rightmost bit after doing the mask. So for this example here, the value of A should actually be, well, this gets turned into 000, right? So the value of A should actually be, since it's shifting by 1, 0, 0, 0. And for this one here, we do have that flipping the ones bit. So the value of A, when we're shifting 3, is 110, 010. Okay, I'm hoping that I can do this with 6 bits for everything. But there are 8 steps in a program. Let me think about that. So register A is an int, it's a 32-bit number. There are 8 steps in the program. Each step uses like 3 bits. Yeesh. Oh wait, there are 8 steps in the program. Well, well. Oh, I think I see how we can kind of reverse engineer this. Let's think about, so what we have here with the 3. We'll get there. A is very likely larger than 32 bits. Unless I mean each three is supposed to be the next three, then maybe it's fine for it to be 3 times 8 bits, 24 bits. No, not 24. 3 times 8, 3 times 9. There are 9 instructions in the program. Oh, no. But we need to output 16 things. So I probably have to change that to long. I probably have to change that to long. Okay, there are 16 things to output. So let's say 16. And I want to multiply by 17 in case the things are overlapping. Maybe, right? We might take 6 bits at a time. Like an easy way to write this number would be 6 bits at a time. But maybe it's 3 bits at a time. Well, we're always shifting by 3 bits at a time. Yeah. 16 times 3. 48 bits. Or 17 times 3. It's 51 bits. We'll need a 51-bit number. Tried it for 6502. And it can, oh, 6502 assembly. I don't know. There's not as much assembly on Stack Overflow. Uh, okay, so we keep getting sidetracked, but this is us outputting the three, and end result here we have the ones bit is flipped, so 0, 1, 0. And if it's shifted by 3, so it's 101. Yeah, 101, 0, 1, 0. But now after we print that 3, we strike out. How do we make sure we print 0 afterwards? So let's say we have 101, 0, 1, 0. This outputs a 3, and then we get 101. And from that 101, we must then, whatever xxx is, we have to use that to output a 0. Okay. From here, I think the search is easy. This is pretty workable. The question is, should I use my CPU implementation, or should I straight up just write this in Scala? If I write in Scala, I run the risk of introducing a bug, I suppose. And if I write it in this machine code, or if I run this program here, then I get cool points. So let's go for the cool points. Implement an LLVM backend for it. But it doesn't have much memory. You only have a couple registers. You needed an expanded instruction set, like turn it into a 4-bit at least. Just infinite registers. Of course. Wait, it has infinite memory? Wait, does this have infinite memory? In what sense? Medalim, how's it going? Well, we're doing part two of day 17, and I think it's going well because I think I understand the program, right? So I was just whiteboarding for a little bit, figuring out what needs to happen to get the numbers I want to show up. And I think I have a strategy, and it's just going to be by shifting three at a time and reverse engineering those numbers. No way to increase any value. All right. Uh, okay, so let's go. I think I'm ready to implement the search. So that's how it's going right now. So we have our program, and I think basically we give our start state a different A. In fact, we can test the stuff we discovered on the whiteboard, right? So we discovered that to get 0, um, we can do this value or 110010. So let's test that. So start state. Let's just define a CPU actually. CPU. So A equals 0B 11. What is that value? 110 010. B just equals 0. I'm just going to condense this a little bit. B equals 0, C equals 0. IP is always 0. And then program is start state dot program. Okay, and let's get the end state of this. So, or actually, we just want the output. So the output of running the CPU. Um, we have two outputs, 0 and 2. Interesting. Right. So 0 was our first output. This did output 0 like I liked, but this 110 at the start is going to be a little bit of a pain. Hey, Metalum is here, and Fizzbuzz and Akari. Um, oh, what did Akari say? Blows your mind to know that there's a whole set of these problems. It's very challenging coming up with an efficient way to solve P2. It takes some real effort. Yeah. I mean, this is the kind of stuff like this, the day 14 part 2. Um, this is the kind of stuff that makes that sets Advent Code apart from like other puzzle sites you might have. The whole Encode series in 2019 was like this. I can't remember what does anyone remember what problem it was last year where we had to basically reverse engineer. Um, what was it even doing? I solved it by like implementing a graph. AOC makes you wait. Yes, that too. I mean, you don't have to wait to go back in the past. Um, so after this as so I think for it to end at 0, we need to have C be 0. Or whatever's to the left of here. Let's try doing this with um the other thing, 1001. We could do those leading zeros if you want. 4 4. Interesting. Metal, thank you for the follow. The first problem like this I ran into was 2021, day 24. That was so fun. And I solved it literally like I don't know, 5 minutes before midnight. Maybe not 5 minutes, but very close to. I get it. If I take out the operations using the seed register, maybe I'm on something. Great, great. So I think we're both onto something. Let's see where this goes. So I can kind of brute force here. Where am I about? If I want C to be 0, let's just try this with all possibilities for what B is. Right. So if we ran that, yeah. So let's do for 0 until 8, and so for A from 0 until 8, we're going to do the output of equals A. Everything else is the same. Yield the output of that. So val candidates, I guess. Let's see what we get. Do any of those result in 0? Heh. Yeah, so we just get the one that results in 0. Great. So we want candidates dot index where this dot head equals 0. Wait. Okay. 4. Okay. So that tells me that if we run this here, 0, 0, 0, 1, 0, 0, this should print a 0, right? Okay. This puzzle reminds you to the Quine circle with 128 languages. Oh, yeah. Um, all right, so that's the last thing that gets printed. Now 100 needs to be our C in the next step, right? So doing this manually, we have 100 and then we have like XXX. So we're gonna do another one of these things. So for A from 0 until 8, we're gonna yield. You know what? I'm gonna turn this to map statement. Let's just do 0, yeah, 0 until 8 dot map. Now we need to take we need to basically append to the left 100. So we're gonna take A plus 0B100 shifted left 3 times. Let me make sure that's valid code. It's been a long time since I've used a bit shift. Shift 32. Is that right? Let's do 2 binary string on that. 2 binary string. 1000000. Okay. So this being the previous number 4, right? So the first one is 4 or 1000. So we take A plus that and we put A into here. And great, so one of these should result in not a 0, but the digit we're looking for is comes from our input. Where's our input? From start state.program. Start state.program. The second to the last value of that. So we want to get a 3. And is there even a 3 in here? Yes, there's a 3. It's the very last one. So that next chunk, what's the word for a 3-bit number? I'm calling these chunks. When I say chunk, I mean that next 3-bit number. Okay. So we messed around enough to kind of see how this is working. I think this will look great. Let's actually write our search. So do want to start from the end. So we're gonna take start state.program, and then we're gonna reverse it. And I think we'll fold left to construct our number. Or maybe, yeah. So when we first start, we had 0 that we want the remainder to be like a 0. So that's going to be part of our state. What else? Wait, is that enough? And we'll call that C. Octal. Oh yeah, octal, of course. Wait, we reverse. We're gonna fold left. 0. And then we have case C, and then we have a target number. We'll just call it N. Or D for a digit. Okay, now C is the value we're kind of checking in, right? So we take 0 until 8. Dot map. These are potential values for A. And A should always be, so in this case, this is the C. So we take the CPU for the start state program. A is going to be, oh, wait, B and C carry over, don't they? No, they basically get overwritten every time, right? They get written before they're used. Let me double check that. Scratch 4. Yeah, the value of B is never really used, so it doesn't matter what we set it to here in this worksheet. So that B and C can be 0. A is going to be A plus C shift left 3. And this becomes the next C, right? Yeah, it becomes the next state. And since we want to do all the intermediate states, we're not going to fold. We're going to do a scan left. And we can figure out that this one here is going to be 7. We can test out this code and make sure we get 7, 4 as our octal digits. Octets. Octal. Octets. Octal digits. Yeah, I guess it's octets. A word. I don't need. Oh, yeah, word. Right. Word two. Um, what are these? These are our potential next C. Well, next C. And what did it have to equal? So we were checking. Hold on. I have to take a look at what I was doing manually. So when we were doing this manually, I want it to equal 3. Okay, so it has to equal the digit. Um, yeah, and then A has some leftover after this runs. And that becomes a new B. Okay. Why are we calling this the A value? This is actually the B value, or the value that will go into B. That's why yeah, I'm calling it B because it's going to end up in the B value. This thing is what's going to end up in the C value, right? Let's not mess with that there. So here in this program, 0 until 8 are the B values that we are trying out here. Such that the result. So we're going to change this into find, not find. So find the case where running that equals vector vector of just D. Let's see it running again in action. So we have A equals 0, B 1, 1, 1, 1, 0, 0. List 1, 3. Oh, that's not what I wanted. Okay, so the output of this here resulted in 1, 0, 0. Oh, no. 1, 0. We swapped the order. This results in 3, 0. Okay. So the desired next C is what we use to choose the 4. So the desired next C was a 0. So the constraints next C should be 0. Output will, I guess the output here doesn't matter, just whatever the next C is. So we're running it once. Okay, and then knowing what the previous one was. So now we have a constraint on our program. So we're going to do, I think we're going to do like 2 chunks for each test. So next C, or rather C, should be C should be 100. So next B should be 0. Next B should be 100. And basically we're able to run that by having, I don't know, trying all of these with that 100 ahead of it. Okay. Next B or also known as C. Let's not give this a value yet. I'm glad people enjoy the speed contest, but my primary goal is to help people learn. So that's my favorite part. Yes, I've seen at least one iteration of your talk about about that first year and needing to scale. The most recent one. I'll take a look at that. Um, I can feel that. Oh my God, it's 3:30 a.m. Jesus Christ. My last brain cells are gone a long time ago. Okay, okay. So if we're doing this thing I'm doing manually, it's very simple. I should be able to automate it. C. So C gets left shifted 3. C was a previous thing. So that should be, does D even matter? Yeah, because that's the digit we're trying to output. And what I'm running into 3, 3, 0. 3, 0 isn't, I guess the head of that output should be 3. So dot head equals D. Okay. So we find the B such that that's that. And I guess B dot get. So that becomes our new C. And do we just let that run? Oh, A is B here. Head is not a member of that. Oh, we have to get the output of that. Um, so output of the CPU. Dot head equals D. At some point we have dot get. Right, so at some point there might be multiple answers. And I guess we do have to search through a tree, don't we? Not just one at a time. Let's keep going to see what that would look like. So to get the next digit, which is a 5, I mean, yeah, there's been interesting stuff to learn every year. Uh, what are we doing? We do 0 until 8. Let's do this kind of thing. And I guess now we want to see, we have this stuff on the right. So and then we have 3 more digits. So this is the bit that we're shifting right. And we output that. I'm just gonna comment this out for a while. Oh, but hold up. We want the one where the output contains the thing we're looking for. So here, where did we find out that the second one should be? Here, we had a list of outputs for 100. Oh, this is assuming that we have 000 in front of it. This is how we decide to get to 3, right? Yeah, fastness asleep. Uh, Index of all past AOC organized by topic. Oh, that's great. That's great. Excellent. I'm gonna check that out. For a couple of reasons. Like sometimes I want to practice a topic. Like it'd been nice to warm up on Dijkstra at some point. But sometimes I'm looking for a past problem. Yesterday on someone's stream, someone was complaining that 16.2 is bad. It's all okay unless it's VM with manual input parsing part. Nice. Um, Wait, this does work though. So here we were searching for something with the output 3, right? No, but something with an output of 0. Right, and that's how we got the 4. Okay, so my thoughts aren't as clear as it should be, and I think that means I should be rewriting what's going on here. So when we're searching for this, we're searching for this in this first step. We're basically taking 0 until 8 dot find an A such that A plus 0 shift 3, sure. Then there, such that the output of this um, equals 3, or no, equals 0. Dot head. I know, this 0. No. Well, let's just do map then. Map to get the output. order of operations here might be messing me up because it should be 4. 0, 1, 2, 3, 4. Okay, so this bit here, I think you need parens. Okay, and we get a 4. Okay, so that's gonna mess with me. Let's go back here and add that in actually. Add the parens in. Um, okay, still have an issue. Pencil and paper, pen and paper puzzles. Cool. Oh, an actual paper cube. Uh, yeah, should have done that. Wait, was that last year or was that 2 years ago? The cube that we fold? I feel like it was 2 years ago, but I don't know. It blends together. Um, okay, so we had a 4. So we were looking for this shouldn't be called A. This should be called B. So B plus 4 on 3, and this needs to equal 3. Um, do we not find anything here? Running infinitely. Let's start with a map. So let's map, see what we get. Not found B, right? Okay, these are lists ending in 0. So at some point, at a couple points, we have 3, 0. So we have 2 options. Ah, yes. Okay, so this is where we start having multiple options to check. Okay, and if the next number we're trying to get, again, so start state that program, let's print that. The next number we're trying to get is 5. So these two, let's do a filter where we get list 3, 0. 5 and 7. Okay. So now we can do this map twice. Once is 5 and 7. Right? Is that what we want to do? Um, well, this prints 2 things. 4, 0. Do we need to do... I want to do it in such a way that I can just use that one bit. Um, so the next one should be 3. and then like constructing that, how to construct that. So 0 left shift 3. Um, hold on, this can be 6 actually. 6. And then 5 or 7. Well, hold on, 4. Yeah, we don't need to do a 0 left shift 3. So we have 4 left shift 6 plus 5 left shift 7. I'm wondering if we also need to do plus 4 left shift 6. I'll have to think about that. Plus 4 left shift 6. And I want to know if it matters. So they will all end in 30, right? And the first digit is 0, 4, 3, 5. 0, 4, 3, 5. But if we do get rid of that, um, let's compare them. So val foo1, val foo2. Okay, so let's print those foo1 dot zip foo2 for each print line. Okay, so this is the full number. 0, 4, 3. Yeah, they do all start with the same number. And we don't care what the second number is, because that first number will give us the behavior that we want. Or that first number will indicate that we're behaving the way we want. Nope, maybe I'm lying. 0, 4, 3, 5, 1, 3. Okay, so we do have to have basically the 4 plus 6. So we take the running prefix then, right? And we left shifted 3. Take the running prefix and we left shifted 3. This note, I think it's about time we write a function. So def, so given I have a current number that returns what you want. And if we want to, let's call this back solve. So we have a desired prefix. As an int, or actually, it's going to be a long, isn't it? Remind me to change my CPU register types to long. So prefix is going to be the long, and then we have a target number. And I guess we have a list of values that it should match with to tell us that we have the right thing. Expected. So listed int. Or hold up. Yeah, this n isn't necessary. Okay. And then this just gives us an int. And to do this, essentially take output So for B, or rather 0 until 8, what would you call, yeah, an octal bit? I don't know what to call an octal bit. A letter, if it's a word. So we want to filter all possible. It's going to be a list of int. So filter for i's such that I plus prefix left shift 3 such that the output of this is equal to expected. Found long and we required int. Yeah, I think we should just change this now. Long. All right. Well, thanks for stopping by, Eric. Always fun to have you. Eric also goes to bed at 4 a.m. You're not alone. Okay, we change things to long. Combo. Does combo have a... You're not going to bed for a while. Okay, you're that kind of all nighter night owl. These things like clean your kitchen. I see. Um, Mind me. Combo operand. What type do operands have? Okay. Um, Program IP plus one int. And it doesn't like this because this is not an int. So we do a mod 8. Um, and I guess we 2int that. A 2int mod 8. I take a mod 8 to int. Sure. Okay. So we have mod 8 to int. Is everything else fine? I think when we're parsing, where do we parse? Input. We should parse. I mean, the parsing's fine. We just upcast that to long. As long as we can work here. So um, found an index seek, we required a list. So output returns a list. Oh, let's make this a vector. Oh, wait, at the very end, we need a list. events dot to list. Sure. Um, expected probably should still be a vector. Okay. Um, now we can back solve something that's long. So this is used in a single step. We have to figure out how to pass it the prefixes. So we take our start state program, and I guess we take the tails. So the first expected output is 0, then 3, 0, 5, 3, 0, etc. Okay. Um, and where do we get the prefix? I think basically from this list of ints. So it's like all the possible values so far. We probably should do the mapping here because this gives us a new set of prefixes that work for the next step. So let's do dot map. Oh, hold up. We do still want to keep I. So I to this thing here. And I. So this is our A value. Okay. So now each time we run with these, we're getting like a bigger and bigger number, so we can fold left. Let's see that tail. So this is what's expected at each step. Dot fold left. I can't help but feel like there's I'll want to refactor how I iterate over this later. So what's our start state? I guess the prefix 0L. And then I guess we back solve with that prefix and that expected. Fold left to back solve. And then that returns a list. So this should be actually a list of 0L. And then we back solve for everything in that list. So we have possible prefixes, prefaces. We'll call them prefixes. And then whatever's expected. So we can take those and we can flat map across them. Dot flat map. And we back solve with that prefix and expected. All right, that gives us our new set of prefixes that we need to check with the next one. And once that's running, okay, we had a problem. Uh, Found list of long and int required an int. Oh, yeah, to list dot map. We only want to keep, no, we don't want to keep the I. We want to keep the A dot map, the thing that was passed in, which becomes the new prefix. Okay. And I guess this should return list along, shouldn't it? Okay. Um, geez, am I doing that right? So let's run this just a few times. Back solve, the prefix is 0, and we're expecting a vector of 0. Oh, A being, we forgot to add. So I plus that. Let me just comment this out a bit. Right, 4 is what we should get there. And next up, you'd have 4, vector 3, 0. And then for the next step, we can have 37 with vector 5, 3, 0. Or maybe we're doing 37, or sorry, 39 with 5, 3, 0. Only one of them progresses, and we get 299. Okay, so that tells me this should work. Oh, we have multiple answers. Oh no. I wasn't expecting multiple answers. Well, I mean, let's try one of these. Val Anses. So ans.head. We want to try the output of that. So let's output the whole CPU thing. Okay, this is the resulting output. And again, start state dot program. That's it. 2411751. Yeah, 2411751. What was that? I mean, okay, it's an answer, but why do we have multiple answers? Wait. Are they all the same? We should do like a dot distinct at each step. So after we flat map, let's do dot distinct. We still have multiple answers. All right, well, let's try one of them. Val adds to equals foo.makestring, comma. Copy that worksheet output. Scratch 4, we don't need this anymore. Hands 2. Here's our string. Wait. I was just about to put my program back into it. What's the actual question? Lowest possible initial value. Okay, lowest possible initial value. That's why. So there are multiple answers, but you want the lowest. Day 17 worksheet. So ans2 equals ans's dot min. Okay. Great. Got it. Cool. That was fun. How did I do? Well, I made up time for part 2. A lot of people were less persistent than me. Um, great. Now I want to refactor this slightly before committing. You're solving second input now. Cool. Um, so input opcode. My CPU class, I'm pretty happy with. I wonder if I should just make this a byte. Oh, whatever. I mean, even a byte's 8 bits. I don't think we have a nibble or anything. Next, we have some sort of output, which is also going to be an 8-bit, right? The outputs are also 3-bit. Octal. So we have a start state, we have an output, and final state helpers. I feel like this I should just place in as a method in our state. Yeah, I would like those as methods. Um, but that's not the important thing to fix right now. Just get rid of some of this test code. Able to quick commit as is solved as solved. So, of people still working on it, how is that going? And who's still in here who is finished? I'm curious what your exploration was like. I see Black Deep stalled out, and Madeline is working on it. Fubar QJX. Fubar Quicks. I don't think I've seen you before. Welcome. Okay. You're only at day 10. Cool. Working along with it. Well, welcome. Yeah. Once you there's a lot more ahead. There's some fun ones up ahead for you. So I hope you get through to those. Metalimi disassembled it, made a formula, recursively generated A starting from n to 0. Okay, so same thing. Um, okay, I'm gonna remove some of this test code I don't need. I took way too long to write this. I just can't keep context in my head when I'm so tired. Um, so we have this backsolve method. I feel like there should be an easier way to a nicer way to write this. I don't like doing tails, well, whatever this is. Like I want to go through the output one at a time. But I guess that's fine. Um, this method, I could perhaps give a name, or maybe I could incorporate this into backsolve. So given that you backsolve with a list of possible prefixes, give another list of possible prefixes. No. Okay, I think that's fine. And I'll leave my tests in here, like my original tests. All right. Scala looks good. It looks good to you. Okay. Thank you. Glad you're liking my Scala code here. Um, what are you liking about Scala? Are you finding this readable? I try to be readable, especially when I'm on stream, but it's hard when you get in advent code mode. Um, you kind of just make a mess as you go. It's like you instinctively want to write spaghetti because somehow you feel like spaghetti is faster. Um, let's check the leaderboard and then we'll see if there's someone to raid. This time of day, the Europeans should be coming in. Okay. So, yeah, it does seem like a lot of people um, maybe are calling it a night on the gold on the second. And let's see what happened here. Yeah, plenty of people have finished part one and haven't done part two yet. I was number 21 for part one. I thought I was going to have a fast delta. That still took 2 hours. I feel like I'm just slow because I'm tired. What's my board ID? 1 second. There it is. And what else do I have? So all my code for the past days, if you're curious, is here. And if you want to share code with me, um, here's my Discord. Oh, that link's outdated. I should have updated to 2020. It's all in the same repo. Oh, and I have some links from Eric to check through in the history. So that'll be fun. Um, and I'm going to take a peek at the Scala leaderboard. So Scala leaderboard isn't as competitive, but still fun nonetheless. And I'm the fourth to finish today. A few people still working on part two. Okay. Refresh. Oh, refresh? Did you just finish? Which one's you? I don't know. Exit. Ah, there you are. There you are. Great. Um, so I can see here how you did today. Maxim. Wait. I'm gonna start by part two. Because you finished a little while ago. I'm not seeing you on the Delta Focus stats. Let me try that again. Um, nope, it refuses to show you here. I don't know. Anyway, welcome to the leaderboard. And let's find someone to raid. Oh, Soggy Boy again. So we could go across the world to Australia. I see Michael PC Gamers on. Do you want to mix it up though? So let's join Soggy Boy. Oh, did they literally just finish? They just finished. No, they are live. Okay, let me refresh this. It's telling me they're live. They must have just signed off. Let's take a look at the hex tree. Oh, I was mentioned in the chat earlier today. Okay. Yeah, let's check out hex tree. All right. So all the newcomers tonight, thank you for joining my stream. And thanks you all for keeping it lively. It's nice to have company when my brain is moving so slow.